Hi students, welcome to the class. This is the fifth part of the topic applications of derivative. In this class we will be discussing about the concept maxima and minima. This concept is quite important because the questions of 6 marks are asked from this concept. And the name of this concept is maxima and minima. Let's check what are things that we have to learn in this maxima and minima. So local maxima, local minima, absolute maxima, absolute minima. These are the things that we have to learn in this topic. Okay. First we'll start with local maxima and local minima. What do you mean by local maxima and local minima? What are the applications of it and how we are going to find the local maxima and local minima of the function? Let's start with an example. Suppose I have a cardboard box of side 18 cm. A cardboard sheet of side 18 cm, like this, right? So this is a cardboard sheet. Suppose this is a cardboard sheet of side 18 cm, and I have to make a cardboard box out of this cardboard sheet. So how I'm going to do this is I'll cut off squares from each corner. I'll cut square from here, and from 4 corners I'll cut squares, and I will fold up the flaps. Okay, maybe you don't understand. Just 1 minute. Okay. So this is our cardboard sheet. Okay. So how I'm going to make the cardboard box is I'll cut off squares from each corner like this. Okay, so now I have cut off squares from each corner. Now just I have to do is what I have to fold up the flaps, right? So I have just folded up the flaps, and the box is ready. So this is our cardboard box. Now the problem is we would like to maximize the volume of this cardboard box, and you know the volume of the box is volume is equal to length into breadth into its height. Length multiplied by its breadth multiplied by its height. So, okay, suppose I'm cutting a square of 1 centimeter. Okay, suppose I'm cutting a square of 1 centimeter. 1 centimeter, since I'm cutting square, so 1 centimeter will be reduced from here and from here. So the length, breadth and height of this box will be, the length will be 16, since 1 centimeter is cut off from here and 1 will be cut off from here. Like that, breadth will be also equal to 16. One gone from here and 1 gone from here, so that is 16. And height will be the side of the square itself. Okay, this one will be the height, right? Since this is the side of, this is 1 centimeter, then the height will be this 1 centimeter, right? Now our volume will be equal to 16 into 16 into the height 1. 16 into 16, 256 into 1 is equal to 256. Suppose I am cutting a square of 2 centimeter, the volume will change. The volume may increase from 256 or it may decrease from 256. Let's see what will happen. For that I am drawing a table here, and let us find what will be the volume at each and every instant, at 1, at 2, at 3. Let's find out. For that I'll be drawing a table here. So this table shows the volume at when the side of the square is 1 centimeter, 2 centimeter, 3 centimeter and 4 centimeter. At 1 centimeter it is 256. When it was 2, the volume is 392. See, you can see that volume is increased. the side of the square, if the side of the square increased from 1 to 2, the volume increased from 256 to 392. And at 3, the volume was 432, and at 4, the volume was 400. So what happened is the volume decreased after 3. At 3, the volume was maximum. So maybe the volume of this box will be maximum at when the side of the square to be cut off is 3, but we are not sure since I have taken only the integers. Maybe answer is 3 or answer will be somewhat close to 3. Then what I'm going to do is I'm going to mathematically modulate this problem. Like since we don't know what should be the square, what should be the side of the square to be cut off, so let's take the side to be x. Okay, let the side of x centimeter should be side of the square of x centimeter should be cut off. Okay, then the volume which depends on x will be, let's take this volume as a function of x, where x is the side of the square. So length will be 18 minus x from here and x from here, so 18 minus 2x. So length is 18 minus 2x. Since this is a square sheet, the breadth will be also equal to 18 minus 2x. So volume, which is length into breadth into height, will be 18 minus 2x into 18 minus 2x, which is 18 minus 2x whole square into x. Okay, on squaring this and simplifying, you will get 324. So 18 square is 324, and multiplying this x, so 324x minus 18, 236 and 72x square plus 4x square into x, 4x cube. So this is volume in terms of x. So we need to find what will be the maximum value when so at what value of x this volume is maximum. Okay, for that I just draw the graph of this function. Okay, so I'm going to draw the graph of the, I observe this, I check the graph of the function in a software GeoGebra. Okay, GeoGebra. You can, this software is very useful, which plots the graph of the functions. And the graph seem to be, okay, I'll draw the graph right here. Okay, so the graph seem to be like this. At 3, it was 432, it was maximum. Okay. And at 9, it was, I seem to be minimum. This point was 3, and this is 9. And graph was somewhat like this, not exactly, graph was somewhat like this. And what I observed is, when at 3 centimeter, at 3 units, this was 432. Okay, and at 9, this was 0. This is the y-axis, it was volume, and x-axis, it is x itself, means the side of the square. Okay, this point 3, 432, 3, 432. This point is point of local maxima, which we discussed earlier. Point of local maxima. Local maxima means at this point, we can't say the volume is maximum at this point. The volume is raised above this 432 when the values after 9. After this value 9, the volume has just rise above 432, right? But we can't cut a square of 9 centimeter or above 9 centimeter. Suppose this is 18 centimeter and we are cutting square of 9 centimeter. What will remain? Nothing will remain, right? 9 centimeter from here, 9 centimeter from, which is not possible. It is not possible to cut the square of 9 or above 9 from this 18 centimeter square sheet. So we can't accept this value. This is said to be local maxima because the volume at left and right of this 3 is lesser than this 432, right? When it is just below 3, this is the volume is lesser than 432, and after 3 also the volume is lesser than 432, and this 3 is locally the maximum, right? The volume goes above the value of the volume. Okay, not volume, we can't say the volume. The value of the function goes above 432 after this 9, but locally this is the maximum. 3 gives us the maximum volume, 432. Right. So how will we find this point 3? Okay. How will we find this point 3 which is the local maxima, and here this point 9 is the local minima. Okay. Since you can see that the volume is below at 9 the volume is 0 and the volume is below 9 at lot of points, right? Volume is below 0 at lot of points, right? But this point is locally the minimum value, because from at the left and right of 9 the volume is above 0. At this point the volume is 0, but at left and right the function value is above 0. So the 9 is the locally the point of minima. So how we are going to find this local maxima and local minima? Let's check out. So in order to find this point, what we have to do is, okay, see, at this point the local maxima, and at this point, which is the local minima, this is the local maxima, and this is local minima. At both these points, we know if we draw a tangent at this point or at this point, okay, the slope of this tangent is 0, since the tangent will be a horizontal line. The slope of the tangent will be 0 at local maxima and local minima also. Okay, and the slope of the tangent, you already know the slope means slope. The geometrical meaning of slope, it was derivative. So derivative is equal to 0 at local maxima and local minima. So what you have to do is you have to differentiate and equate with 0. On solving this, you'll get points like local maxima and local minima, right? Because the derivative, the value of derivative is equal to 0 at local maxima and local minima. So you just differentiate, equate with 0, you will get local maxima and local minima, and also you will get the point of inflection that I will discuss later. Okay, point of inflection, not that point. The point of inflection I will discuss later. So you have to differentiate this and equate with 0. So I'm going to differentiate this. V dash of x is equal to 12x square minus 144x plus 324. Okay, so I'm equating this with 0. So let us solve this, taking 12 in common. So what remains is x square minus 12x plus 27 equal to 0. X square minus 12x plus 27. On solving this, you will get x equal to 3 or x equal to 9. On solving this quadratic equation, you will get 3 or 9. So we got this point 3 and 9, which was local maxima and local minima. Okay, but maybe we are not sure about which is local maxima and which is local minima. In this question, it's okay. We already draw the graph. We found the volume, and we know that 3 is the local maxima. But if you are provided a question and you are asked to find the local maxima and local minima, you should know which point is local maxima and which point is local minima. And to figure out that, we have two tests. First derivative test, and second derivative test. Okay, so let's see what these things says, the first derivative test and second derivative test. Okay, let's see what is first derivative test. Okay, in first derivative test, you will be provided a function f of x, or maybe you have to derive a function f of x, that we have derived a function v of x here. Okay, according to the situation, you have to derive a function. Okay, then you have to differentiate the function, find f dash of x, like we have found v dash of x here. Differentiate it, then equate that with 0. F dash x equal to 0. Equate that function, the derivative equal to 0. We have done here. This is the derivative, and we just equated it with 0, and you have to solve it like we solved it and found the points 3 and 9. While solving this, maybe you will get the points like this. Suppose this is the solution, x1, x2, x3, and goes like here. Only we got two solutions. Maybe you will get more than two or more than or maybe you will get infinite solution depending on the nature of the function. Here this was only a cubic polynomial, that's why the derivative was second degree and we got two solutions, right? Maybe you will get more than two solutions. Okay, and we have to check whether this point x1 is point of maxima and point of minima using this first derivative test. Okay, let's see how will we do that. Okay, suppose this x1 is local maxima as shown in this figure. Suppose this x1 is point of maxima. The value of the derivative will be positive. Value of the derivative will be positive, which for the values which is close to x1, which is in the left of x1 and which is very close to x1, and value of derivative will be negative for the value of derivative will be negative, which is close to x1, which is the right of x1, right? See, the value, the derivative, because the derivative means slope, we'll get a positive slope, for the value which is very close to x1 on the left side, and a negative slope because the function is increasing on the left side of x1 and the function start to decrease after the value x1. So the derivative will change its sign from positive to negative. So positive, okay, positive to negative. Derivative will change its sign from positive to negative while goes through x1 from left to right. The derivative will change from positive to negative, means a positive slope to negative slope. Then that point x1 will be a point of local maxima. Okay, let's check out in this problem. See, I'll factorize this derivative once again. Suppose this is 12 into x minus 3 into x minus 9 equal to 0, and after that I got x equal to 3 or 9, right? So this 3 is local maxima. We can say this 3 is local maxima by first derivative test, since suppose let's take the value, this is 3, okay, this is 2 and this is 4. For the value which is very close to 3 and on the left side of 3, say 2.9. So what is the derivative? What is the sign of derivative? Is it positive or negative at 2.9? So 2.9 minus 3 means it will be negative, and 2.9 minus 9 is also negative. So negative into negative, right? 2.9 minus 3, a negative value. 2.9 minus 9, a negative value. So negative into negative makes this positive. So at the value which is close to 3, on the left side of 3, it was positive, and right side of 3, let us check for the value 3.1. So 3.1 minus 3 is positive value, and 3.1 minus 9 is a negative value. So positive into negative, the derivative is negative, so negative derivative here at very close, which was 3.1. So the derivative changes its sign from positive to negative. That means it increased, then it started decreasing. Then this point is point of local maxima. Like that, if f dash s changes its sign from negative to positive, that means the function was decreasing, then it started increase like this. Then this point will be a point of local minima, right? This is how we will find local maxima and local minima. And using first derivative test, we can also find the point of inflection. Point of inflection. Okay, that we have discussed earlier, right? The point of we haven't discussed, but I have said this term, point of inflection. Now we will be discussing about point of inflection. Let's see what is point of inflection. Okay, inflection. And how will we find the point of inflection using the first derivative test? Here it goes. Let's see what is point of inflection. Suppose this is a graph of a function, x axis, y axis. This is the graph of the function. Okay, like this is the point x1, this is x2, and this is x3. Okay. See, you can clearly see that x1 is a point of local maxima, x2 is point of local minima, and then what is x3? This point. See, at x1, x2, and x3, at all these points, the tangent is horizontal, or the value of the derivative will be 0. F dash of x, or dy by dx, equal to 0 at all these points x1, x2 and x3. x1 and x2 is point of local maxima and local minima. Then what is x3? x3 is neither the local maxima or nor a local minima. Now what is it? See. The function was increasing before x3, and after x3 it is again increasing, right? It doesn't started to decrease, right? This kind of point is said to be point of local maxima. The derivative does not change its sign. See, from considering the value of x from left to right, the derivative of the function has not changed its sign. It was positive since it was increasing, then it was positive again. The derivative will be positive because again the function is increasing. For example, suppose we have a function f of x equal to x cube. You know the graph of that function, f of x equal to x cube. This is the graph of f of x equal to x cube. So derivative of x cube, f dash of x equal to 3x square. 3x square, our derivative equal to 0 at x equal to 0. At x equal to 0, y also 0. So this is that point. See, at this point, derivative is equal to 0. But before this point and after this point, the function is increasing. The value for which is close to left of 0, let's take it negative 0.1, the derivative will be, if we substitute here, we will get a positive value, right? Because here it is square. And if you are taking 0.1, positive 0.1, again you will get a positive. That means derivative is not changing its sign from left, not changing its sign from positive to negative. It is positive, then again it was positive. Okay, so it is not changing its sign while taking the value of x from left to right. That means this point is point of inflection. So it is clear, this is point of inflection. Okay, now let us conclude what all things that we have learned in today's class. Okay, so in today's class we discussed about local maxima, local minima, point of inflection, and how will we find these points with the first derivative test. For that, let's see what is the working rule. First, you have to derive a function in the form y equal to f of x. Then differentiate that, find f dash of x, equate it with 0, solve to find the point of local maxima, local minima, and point of inflections. You solve this f dash x equal to 0, and you got x1, x2, x3 as a solution. Then x1, x2, x3 may be point of maxima, point of minima, and point of inflections. So how will we figure out that x1 is point of maxima? For that, you have first derivative test. Okay, what you will do is you check whether the f dash x changes its sign from positive to negative or negative to positive as we increase through the value of x. If f dash x changes its sign from positive to a negative, then the x1 is a point of local maxima. If it changes from negative to, you just remember this figure, positive to negative, point of maxima, negative to positive, okay, point of minima. Does not changes its sign, okay, does not changes its sign, means it is point of inflection, right? So remaining part of this concept we will do in the next video. In the next video we will be discussing about first we will be writing the notes from this concept, maxima and minima. Then we'll go to the second derivative test, and also we have to discuss about the about local maxima and local minima at points where the function is not differentiable. See, at this point the function is not differentiable since we can draw more than one tangent. This we explained while taking the chapter continuity and differentiability. Here we have a point where we can draw more than one tangent. So at this point the function is not differentiable. and this point also, this is also a point of local maxima, right? You can clearly see that this is a point of local maxima, but here the function is not differentiable. So we'll discuss all these things and we'll write the detailed notes of this concept in the next video. Till then, bye.